September 7th, 1940, 8 p.m., 15,000 feet above London. Hauptmann Klaus Meyer banked his Heinkel He T-111 into formation with 347 other bombers crossing the Thames Estuary. Below, searchlights swept uselessly through darkness. Anti-aircraft shells burst thousands of feet below his altitude, their timing mechanisms unable to track formations invisible to ground observers. Chain-home radar stations on the coast had tracked the raid forming over France. RAF Fighter Command knew the bombers were coming, knew their heading, their altitude, their approximate numbers. What they couldn't do was stop them. RAF Spitfires and Hurricanes, deadly in daylight, were grounded. Night fighters, twin-engine Bristol Blenheims equipped with primitive AI Mark III radar, prowled the darkness, but might as well have been blindfolded. The mathematics were cruel. Chain-home operated at 10 to 13 meter wavelengths, requiring antenna towers 350 feet tall and arrays spanning acres. Magnificent for early warning, useless for airborne interception. Current airborne radar, AI Mark IV, used 1.5 meter wavelength. Still required antennas so large they protruded from the aircraft nose like tusks. Detected targets at perhaps 3 miles on an excellent night, 2 miles typically, sometimes not at all. That night, RAF night fighters flew over 100 sorties. They shot down 1 Heinkel. 1. Meyer's formation dropped 300 tons of high explosives and 440 incendiary canisters. By morning, 430 civilians were dead, 1,600 injured, and London's docklands burned across 250 acres. While London burned and RAF pilots landed in frustration, after seeing nothing, detecting nothing, killing nothing, 2 physicists at Birmingham University were testing a copper block slightly larger than a man's fist. The device, a cavity magnetron, generated electromagnetic waves 150 times shorter than chain-home. Shorter wavelengths meant smaller antennas, meant radar that could fit inside a fighter aircraft's nose. In September 1939, Britain had possessed no working centimetric radar, no theoretical path to building one, and Germany's radar research was ahead. By February 1940, John Randall and Harry Boot had built something Germany would never match. The problem wasn't detecting electromagnetic waves. Robert Watson Watt had demonstrated radio detection and ranging in February 1935. Bouncing radio waves off a Handley Page Hayford bomber at 8 miles distance. The problem was physics. Antenna size scales directly with wavelength. Chain-home's 10-meter wavelength demanded enormous antennas, making mobile radar impossible. To fit radar in an aircraft nose required wavelengths around 10 centimeters, 100 times shorter. Generating high-power centimetric waves was theoretically understood but practically impossible in 1939. Magnetrons had existed since 1921 when Albert Hull at General Electric invented a vacuum tube that used magnetic fields to control electron flow, producing microwave radiation. Simple. Magnetrons generated microwaves, yes, but at power levels measured in milliwatts, perhaps 1 watt maximum. Radar needed kilowatts, thousands of times more power. Multiple researchers had attempted resonator designs through the 1930s. Japan's Kinjiro Okabe built multi-cavity magnetrons. All failed to produce useful power at centimetric wavelengths. The mathematics worked perfectly. The engineering didn't. Germany should have solved it first. German radar research began in 1935 under Kriegsmarine funding. GEMA, Gesellschaft für elektroakustische und mechanische Apparate, developed Seetakt naval radar. Telefunken's Wilhelm Runge pioneered airborne intercept systems. Würzburg gun-laying radar, operating at 53 centimeter wavelength, would be operational by 1940. Germany possessed funding, facilities, industrial capacity, and physicists as talented as any nations. But German researchers focused on perfecting meter wave systems, not pursuing centimetric wavelengths. They didn't believe centimetric radar was achievable during wartime. Britain's desperation created opportunity. September 1939 war declared, the airborne radar gap obvious and lethal. Air Ministry and Admiralty both demanded centimetric systems. The problem landed at Birmingham University's physics department under Mark Oliphant. 2 researchers were available: John Randall, 36, spectroscopist with an Oxford doctorate; Harry Boot, 27, fresh Ph.D. from Birmingham, theoretically brilliant. Neither had ever worked on magnetrons. They were Britain's only choice, which meant they had to be enough. Autumn 1939, Birmingham University Physics Department. Mark Oliphant, the Australian department head, assigned the magnetron problem to his only available researchers. John Randall brought expertise in spectroscopy and quantum mechanics. Harry Boot provided theoretical calculations. The critical third member was William Butt, the department machinist who could fabricate anything if you explained what was needed. They had no dedicated funding initially, scrounging copper and equipment from departmental supplies. November 1939, Randall and Boot studying why existing magnetrons failed. The insight came from examining electron behavior. Previous magnetrons suffered poor mode control, electrons oscillating chaotically, producing weak, unstable output. The solution seemed obvious once conceived. Machine resonant cavities directly into a solid copper anode block. Instead of attaching separate resonators to the magnetron, make the magnetron itself a resonating cavity system. The cavities would force electrons into stable, synchronized oscillation patterns. Alternating electric and magnetic fields within the cavities would control electron emission precisely. The engineering challenge was unprecedented. Machining copper to tolerances of 1/1000th of an inch for microwave devices had never been attempted. Boot calculated the theoretical requirements while Randall designed the physical structure, but would drill circular cavities into a solid copper cylinder with perfect radial symmetry. Any misalignment would cause mode instability and failure. December 1939 through January 1940, Butt machined the first cavity magnetron. The copper block measured roughly 4 inches diameter, 1 inch thick. 8 resonant cavities arranged in precise circular pattern around the central cathode. Late January 1940, first test. They applied the magnetic field, heated the cathode, applied voltage. Expected output, perhaps 10 to 50 watts. The device fused their measuring equipment. Second test with proper power measurement recorded 400 watts continuous output at 9.8 centimeter wavelength. Within weeks, improvements achieved 1 kilowatt, then 10 kilowatts. Later refinements produced 25 kilowatts pulsed output. This was 1,000 times more powerful than any previous microwave source. The elegance was suspicious. Cavity resonance forced electron bunching into stable patterns. High quality factor. Cavities meant efficient energy extraction. Solid copper construction allowed massive heat dissipation. Simple cylindrical geometry provided inherent stability. Manufacturing was relatively straightforward compared to complex multi-stage amplifiers. Boot later said the device worked almost immediately, which made them nervous. They kept testing to find their mistake. They hadn't made one. Spring 1940, Germany invaded France using radar-directed fighters. Freya early warning radar operated at 2.4 meter wavelength with 120 kilometer range. Würzburg fire control radar directed flak batteries with precision unknown to Allied gunners. Liechtenstein BC airborne intercept radar entered testing at 62 centimeter wavelength. German night fighters, primarily Messerschmitt Bf-100s, began achieving kills over Britain. The Kammhuber line, a radar-directed night fighter defense system, stretched across occupied Europe. By late 1940, Luftwaffe night fighters were becoming genuinely effective. Germany didn't need revolutionary technology. Their evolutionary development was working. February 1940, Randall and Boot demonstrated their cavity magnetron to military officials. Recognition was immediate. This changed everything. But laboratory prototype and mass production were entirely different problems. GEEC, General Electric Company in Britain, received production contracts. Telecommunications Research Establishment at Worth Matravers began designing AI Mark 7 radar to exploit the new magnetron. The new radar would use 10-centimeter wavelength with dish antenna small enough for aircraft noses, targeting detection ranges of 5 miles for bombers, 3 miles for fighters, versus 1 to 2 miles for AI Mark 4. The Battle of the Atlantic demanded attention simultaneously. U-boats were winning. 10-centimeter radar could detect submarine periscopes and surfaced U-boats in darkness or fog. The Admiralty demanded immediate naval versions, designated Type 271 surface search radar. Multiple urgent programs competed for limited magnetron production while the clock ran. Battle of Britain began July 1940 in daylight. The Blitz began September at night. August 1940, Britain made an extraordinary decision. Send the cavity magnetron to America with complete technical specifications. Britain couldn't mass-produce enough magnetrons alone and needed American industrial capacity. The Tizard mission, officially the British Technical and Scientific Mission, departed for Washington, led by Henry Tizard. September 1940, the mission arrived carrying a cavity magnetron sample. American military and scientific leaders were stunned. Nothing in the United States approached this performance. Agreement followed quickly. America would mass-produce magnetrons while Britain shared all radar research. MIT Radiation Laboratory was established October 1940 with the cavity magnetron as foundation. By 1943, MIT Rad Lab employed 4,000 people developing microwave radar systems. The decision to share was controversial in Britain. Giving away war-winning technology seemed reckless, but the calculation was pragmatic. Lose the war alone with secrets intact, or win together by sharing everything that mattered. AI Mark 7 radar entered service spring 1941 in Bristol Beaufighters. The first kill using cavity magnetron radar came July 1941. By late 1941, RAF night fighters were achieving regular intercepts. November 1940, before AI Mark 7 deployment, night fighters shot down 7 German bombers total. November 1941, with AI Mark 7 operational, 68 German bombers destroyed. May 1941, the Luftwaffe abandoned sustained night bombing of Britain after losses became unsustainable. Germany attempted developing centimetric radar, failed, and resorted to electronic countermeasures instead. De Havilland Mosquito, equipped with AI Mark 8 radar, became the supreme night fighter. 10-centimeter radar allowed tight intercept vectors, pilots reporting radar contacts at 4 to 5 miles. AI Mark 10 at 3-centimeter wavelength entered service 1943 with even smaller antennas. By 1944, German night bombers were effectively driven from British skies. The cavity magnetron didn't just help win the night battle, it made the night battle decisive. German centimetric radar development remained sporadic and unfocused. Rotterdam Giret, a 9.1-centimeter naval radar, underwent testing in 1944, too late and unreliable. Germany never developed the cavity magnetron design. One captured German physicist examining a cavity magnetron reportedly said, "If this is what they had in 1940, we never had a chance." John Randall was knighted in 1962, died 1984. Harry Boot remained at Birmingham University, died 1983. Both received modest recognition, but no financial reward. The cavity magnetron was never patented. Boot later said they didn't know they were changing history, just trying to make the damned thing work. The cavity magnetron became foundation for microwave technology. Percy Spencer at Raytheon discovered it melted chocolate in 1946. First microwave oven appeared 1947. Microwave relay towers carry telephone calls. Satellite communications, cell phones, wireless internet, radar altimeters, weather radar, all trace lineage to Randall and Boot. Britain in 1939 possessed no centimetric radar. Britain in 1945 deployed it on every ship and aircraft. The revolution happened in 3 months in a university laboratory. 2 physicists, 1 machinist, scrounged copper, precision thinking. While debates raged about strategic bombing, the war's outcome was decided by a device the size of a fist, built in Birmingham. September 7, 1940, London burning, night fighters helpless. Birmingham laboratory, copper block being machined. That block became thousands of magnetrons, guiding fighters to bombers, escorts to U-boats, bombs through darkness. The Battle of Britain is famous. The cavity magnetron won the battle nobody watched.